So now let's talk about LASSO regression, which stands for least absolute shrinkage and selection operator. It is one type of regression on top of the ones we've learned previously that are the linear and ridge regression. So, like linear and ridge, LASSO tends to optimize a certain cost function. And what is this cost function? It is this one. So instead of an L2 norm, we've got the L1 norm instead, right? And this half is not found over here. So one thing to note here is one of the very, I would say, important features of the LASSO regression is that it tends to completely eliminate the weights of the least important features. That is, it just sets them to 0. So if it finds a feature that is really respectively irrelevant, it adjusts its weight and just set it to 0. It completely forgets about it. And to show you what I mean, I'm going to start with sklearns. I'll import the LASSO just to show you that how LASSO works. It's really the same as Ridge in terms of Python. Instead of Ridge, you type in LASSO. You pass it the alpha that you want, let's say 0.1, right? LASSO underscore regression fit y versus x, and LASSO underscore regression dot predict. Let's say the same value, that is 1.5, right? So let's see what's going on over here. I'm going to use the same function that I had over here, the plot model, to generate similar plots over here in order to, have a feel of how LASSO works, right? So to this extent, let's open a figure. So plot figure, fig size, 8x4. Open a subplot and call the function plot model, passing it LASSO. Let's first set polynomial to false. Alphas, let's pick 0, 0.1, and 1, and a random state of 42, right? This is what I get. Okay, good. Let's label the y-axis as y, and let's rotate it. Okay, now let's plot the polynomial model using LASSO, of course. So the same line I had here, I'm going to copy paste it over here, setting the polynomial to true. And over here, just to see some stuff, let me set it to 10 power minus 5, right? And in the end, I'll show my plot. Okay, good. So as you can see over here, let's focus a bit on the polynomial part. So as you can see, with alpha equal 10 to power minus 5, the curve looks a bit quadratic. Well, let me increase it just a bit, say 0.8 minus 10. Yeah, so you could see that the curve tends to be quadratic. So this deviation over here, we don't care about it. And we have this over here, right? And some may argue that this curve could actually be approximated as linear. In other words, all the weights for the high degree polynomial features are close to 0. So this means that LASSO regression automatically performs feature selection and outputs a so-called sparse model, that is, a few non-zero feature weights. Okay, so that's how you perform LASSO on sklearn. Now, one important thing to notice over here is that if you were to implement a numerical optimization method such as SGD to optimize the g of theta, the gradient of the penalty term is not defined, and instead we'd use the so-called subgradient of the penalty. Now, it is easily seen that this is not differentiable because we've got the absolute value over here. And we know that absolute x is not differentiable at x equals 0, and hence the derivative is not defined everywhere. Instead, we define a subgradient, and hence once you once you want to obtain a gradient of g of theta with respect to theta, you go ahead and optimize. You get the gradient of the MSE as we did previously, plus alpha, and here you get a vector of the subgradients. That is, you get, if you derive this with respect to theta, but taking the subgradient into account, you'll get the sine of each element. That is the sine of theta 1, sine of theta 2, all the way down to sine theta n, right? Where the sine is plus 1 if theta is positive, minus 1 if theta is negative, and 0 if theta is 0. Okay? Now, elastic net is a middle ground between ridge regression and lasso. So up till now, we discussed 3 regression models, that is linear, ridge, and lasso. One more interesting regression model is the elastic net, which is middle ground between ridge and lasso. In other words, the regularization term is a simple mix of both ridge and lasso's regularization terms. And you can, control the mix ratio by R. So you've got an R multiplied by the lasso penalty, and you've got a 1 minus R multiplied by the ridge penalty. That is to say, when R is 0, so R is always between 0 and 1, when R is 0, then elastic net becomes ridge. And vice versa, when R is 1, this term cancels out, you're left with lasso. So when R is 1, elastic is lasso, and when R is 0, elastic is ridge. Okay? So the question here is, when should I use linear regression or even ridge, lasso, or elastic net? Now, in practical scenarios, it is almost always preferable to have at least a bit of regularization. So generally speaking, you should avoid linear regression in real life data. So ridge is a good starting point. So you'd always want to start your regression with ridge by playing around with alpha. But if you suspect that only a few features are actually useful, so if you have prior knowledge that some of your features are relevant, whereas the others are just irrelevant, you'd want to start thinking about lasso because it implicitly performs feature selection, or even elastic if you want to, if you're not that sure of feature relevancy, right? Now, in general, elastic net is preferred over lasso, since lasso may behave erratically when the number of features is greater than the number of training instances, or even when several features are strongly correlated. So let's see how to implement elastic net on Python. So the first thing you'd want to do is that, as we did previously, from sklearn.linear model, import elastic net. Then instantiate an elastic net object, passing it the alpha, and then the R, which is referred to as L1 ratio, because the higher R is, the more L1 you're stuffing your model with, right? So that's why it's called L1 ratio. Let's say it's a 0.5. Let's set a random state to 42. Next, you'd want to fit y versus x, and last but not least, you can perform now predictions. Let's say you predict 1.5, and there you go. Okay? So this is how you get the job done simply with sklearn's elastic net function. Now let's talk about a very important topic, that is early stopping. So I'm going to explain this issue through following code. So let's set the seed first. Let's say I've got 100 samples, right? Generated according to the following. So I've got 6 times a random number between 0 and 1 minus 3, right? And the y is generated according to the following quadratic model. That is this model over here. Okay? Now, let's extract the training, the validation sets, and their targets using the train test split and using the following split. So 50-50 with a random state, right? So I've got the training and test sets over here. And now let's say I am about to perform some sort of polynomial regression. So I'll open a pipeline. I'll specify that my features are going to be learned from a polynomial of 90th degree. And I'll also call the standard scalar, right? So running this. Next, I'm going to train using this polyscalar, right? I'll fit x train, then I'll do a transform, right? And next, let's say, okay, you want to do a sort of learning based on SGD regressor, so an iterative algorithm, by setting, let's say, the maximum number of iterations is 1, so early stopping, and the tolerance, okay, I'll set it to minus infinity, no problem. And I won't specify a penalty up till now. Also, I'll pass the eta to be something really small. That's the learning rate. Warm start, let's say I'll put it to true. Now what warm start does is that when set to true, it reuses the solution of the previous call to fit as initialization. That is, we're saving iterations here. We're making use of previously computed values to initialize again if we come and execute this line of code. Also, you've got parameters such as the learning rate. You can set it to constant, and you can set your random state to a certain seed. So running this, all is good. Now let us fit x train polyscaled versus y train, or the other way around. And for each fitting model, let us predict and predict as well using the validation set. Okay, so let's define some errors over here. So first of all, let's run at every epoch. Let's run over, I don't know, something like 500 epochs, right? Indentation and such. And at each epoch, well, for that, I'm going to define an empty train errors array and an empty validation errors array. So we're just computing the error right now. So at each iteration, at each epoch, I'm going to append an error. That is the mean squared error of y train minus y train predict. So the two vectors, you subtract them, square, and take the sum. That's what this function is doing. And also, you want to compute the same thing for the validation. So validation, y val, and y val predict, right? Run, and there you go. Now the best, so after that, the best epoch on the training set is nothing other than the minimum on val errors. So it's the position, it's the epoch index where the mean square error is minimum, right? Same thing goes for the validation, right? So its corresponding RMSE is nothing other than the square root of the MSE, right? So square root of val errors at index best epoch. There you go. So the best epoch turns out to be at index 239, right? Okay, good. So let's plot on the x-axis from 0 to 500. We're going to plot best. We're going to plot a horizontal line that connects the best val epoch. So it's at level best val epoch. So it's the minimum RMSE obtained by the validation set. I'll plot it in dotted black. And I'll set a line width to 2. That's all we see right now, okay. Next, I'll go ahead and plot the square root of the mean square error. That is the RMSE. I'll plot it in blue. Line width, set it to 3. And I'll give it a label that is validation set. There you go. You can see that it's minimized at best epoch. Okay. What else do we need? So let's plot the training errors. So as I did here, copy paste it. Instead of val errors, I'll put train errors. I'll plot it in red. I'll change the label to training set. I'll plot a legend. I'll set the legend. I'll label the x-axis as epoch index. And the y label as RMSE. And there you go. Okay, good. One thing is to, you can insert an arrow over here saying that this is the best epoch. So you'd want to do this here. You can do it by plot annotate, naming best model, passing it the coordinates of the arrow. So we want it at best epoch and best val epoch. XY text. Now you can see it's messy, right? So the way to lift it is by calling XY text and passing the same coordinates right here, but this time lifting the y by 1, right? So running this, there you go. Now let us center Okay, and let's insert the arrow giving it a face color of black. Okay, let's shrink it a bit, so shrink to 0.05. Good. And now let us give a font size, let's say 14. Perfect. So as you can see over here, we're training a model based on SGD, right? And we can see that as the epochs go by, the algorithm learns and its RMSE on the training set naturally goes down. And so does the prediction error on the validation set, right? However, after a while, unlike the training set RMSE, the RMSE on the validation set goes back up. It doesn't plateau, but it goes back up, which indicates that the model has started to overfit the training data. With early stopping, you just stop training as soon as the validation error reaches the minimum. It is such a simple and efficient regularization technique that Geoffrey Hinton called it a beautiful free lunch. Now, keep in mind that we only had one iteration, right? So this all is being performed with one iteration. So let's see what happens with 10 iterations. You could see that this weird phenomenon over here. So the best model, it's minimized at 350 epoch index. Actually, stuff become even way more weird when you've got 100 iterations. Take a look at that. So it's really overfitting the data. Anyways, we set the max iteration to 1, and hence the best epoch index is over here at 239. So thanks for watching. If you found this lecture beneficial, please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below, and I'll make sure I'll get to it as soon as possible. Also consider donating to my Patreon account any amount you wish. Thanks for watching, and I'll see you in future lectures.